Recall the technique we learned that if log base A of C equals log base A of D, then C is equal to D. So this technique requires that you have a single log on each side of the same base. When this happens, we get to set the inputs to the logs equal to each other. Now, you should draw no slashes through the logs because people start thinking there's multiplication going on where there's no multiplication at all. Also, be sure to check for false solutions. An x value is going to be valid if the following happens. That x value has to ensure that the input to each log is greater than 0 because, again, of the domain of logarithm issue. So to solve log base 5 of 7x plus 3 equals log base 5 of x plus 1, notice there is a 1 log on each side of the equation. Their logs are the same base. They're both base 5. And so we get to set the inputs equal. That is, set this input of 7x plus 3 equal to this other input, which is x plus 1. Just set those equal. Do not draw a slash through the log base 5. Just one line down, just write the input to one log equal to the input to the other log. So the c in our example is 7x plus 3. The d in our example is x plus 1. And then subtract x on both sides, subtract 3 on both sides. You have 6x equals negative 2. Divide by 6 on both sides, and x is equal to negative 2/6. In other words, x is equal to negative 1/3 once you reduce the fraction. Now, are we done? Not quite yet. We just need to check. Take that x value, negative 1/3, and go look and check, right? We need to ensure that this x value makes the input to each log to be greater than 0. So one input to logarithm is 7x plus 3. And when you substitute negative 1/3 for x, you end up with 2/3, which is greater than 0. The other log's input is x plus 1. And if you take that and again plug in negative 1/3 for x, you have negative 1/3 plus 3/3, which is going to be 2/3, which is bigger than 0. That's good. In both cases, the input to the logarithm was bigger than 0, right? Because x equals negative 1/3 causes both of the log inputs to be positive. So the input to the logarithm, to each logarithm, must be positive. And that worked out. So x equals negative 1/3 is a solution. You'll notice from this example that it doesn't matter that the x value is negative. What matters is what happens to the input to the logarithm. So here's the technique again. Now, we have log base 4 of 3x minus 1 equals 2. That can't use the technique above, unfortunately. Right? So what we end up doing is this technique doesn't apply, and so we instead have 3x minus 1 is equal to 4 to the 2 using the definition of logarithm. So simplify the right side as a 16, add 1 to both sides, divide both sides by 3. So you have x equals 17/3. We had to use the definition of logarithm. The technique above wasn't helpful here because we don't have a log on each side. There was just a 2 on the right side. So because the original equation had logs, though, we check. 3x minus 1 was the input, and that simplifies to a positive number. That's good. So we have x equals 17/3 is a solution. Now let's also solve 2 to the 3x plus 1 equals 9. That's also going to need the definition of logarithm. So we reorganize this as 3x plus 1 equals log base 2 of 9, subtract 1 on both sides, divide by 3 on both sides, and as a final answer we have log base 2 of 9, then a minus 1, all over 3. Now, we could rewrite the answer a different way, ln of 9 over ln of 2, to replace the log base 2 of 9 part, using the change of base formula. It's just that this is the type of thing that you would type into a system. The technique, which required one log on each side, didn't apply to either of the problems here. Instead, we had to use the definition of logarithm on both of these problems. And over on the second question, because the original problem didn't have logs, we had nothing that we had to check. So let's compare the techniques we've had. So log base 4 of 3x minus 1 equals 2, the equation we just solved a moment ago, had a log on one side but a constant on the other. So we use the definition of logarithm. 2 to the 3x plus 1 equals 9 had an exponential function on one side and a constant on the other. So again, we use the definition of logarithm. Log base 5 of 7x plus 3 equals log base 5 of x plus 1 had one log on each side. So we use that technique. Log base a of c equals log base a of d. Then from there we would get c equals d. So these were the 3 problems that we just recently did. Not in this order, but just to compare our techniques. And this, I put this one last here because this required a single log on each side. Yeah, the method that we were just using required one log on each side of the same base and nothing else. So for example, we applied the technique, just to repeat it, sorry, to this problem here, log base 5 of 7x plus 3 equals log base 5 of x plus 1. The technique does not apply to log base 5 of 7x plus 3, close parentheses, then a plus 1 equals log base 5 of x plus 1. The reason is because of this plus 1 that's right here. The technique also does not apply to log base 5 of 7x plus 3 equals log base 5 of x plus log base 5 of x plus 1. And that's because there's two logs on the right side. So we'll eventually deal with this plus 1 issue, maybe not right now, but let's take a look at this one, which is actually surprisingly the easier issue to deal with. We don't have a way to deal with it yet, but we are now going to dig into a formula which can turn two logs added together, the sum of two logs, into one log. And then after we apply a new formula, then we'll be able to apply the old method here. So we're going to look at the laws of logarithms. There are three of them. The first one says log base a of u plus log base a of w equals log base a of u times w. The second one says log base a of u minus log base a of w equals log base a of u over w. And then the third one is log base a of u to the c is equal to c times log base a of u. Now you notice in these laws of logarithms, we'll go do that in a second. So what we're going to do in just a moment is, well, first of all, why are these true? What are the common mistakes when trying to use these? So you'll notice, for instance, is log base a of u plus log base a of w is equal to log base a of u times w. Not u plus w, but u times w. If there's a plus here, then it would look like log distributes or log factors or whatever kind of thing that would be confused for multiplication. Again, I keep trying to stress you need to say log base a of u, log base a of w, not log base a times u, right? That would be a mistake. And so common mistakes occur because people somehow, for some reason, think that this first formula has a plus sign on the right side, but it doesn't. It's a u times w in there. Okay, so we're going to look at some common mistakes, and then we'll talk about correct ways to use these formulas, and then use them for the type of problem that we were just looking at. So first, let's take a look at this. The first law of logarithms, just pasted here. Is that formula true or false? Explain. Well, okay, this is phrased more like a quiz-style question, but, well, it is true. Yeah, so what we're going to do is the first term, we're just going to assign to a new variable. Let r equal log base a of u. For the second term, let s equal log base a of w. Well, now, this r equals log base a of u, you can rewrite that using the definition of logarithm. Yeah, so definition of logarithm, you have a to the r is equal to u, and similarly, you have a to the s is equal to w. Well, then what I want to look is, I want to look at just u times w. I just want to consider this expression. Let's think about the expression u times w. So that u times expression, right? Something that is a number. Let's think about what that equals. Well, we can replace the u here with a to the r because, well, a to the r equals u. We can replace the w here with a to the s because, well, a to the s is w is equal to w. So we make some replacements. Then a to the r times a to the s is a to the r plus s. And so if we summarize what we have, we just taking this here, the work in the middle is getting in the way. We've got a to the r plus s is equal to u times w, just copying from the line above. We just ripped out the middle part and then just swapped the two sides. So we have a to the r plus s is equal to u times w. And then if you apply the definition of logarithm to this, you get log base a of uw equals r plus s. And then all we do is we take this equation and leave the one side alone here, but on the other side, there's an r, and we just replace r with how we originally defined it. We defined r to be log base a of u, so right there. And then plus sign, copy that plus sign right here. And then this s here, well, we replace it with how we originally described s. We ourselves picked s to be log base a of w, and we just make that replacement here. So now we end up with log base a of uw is equal to log base a of u plus log base a of w. If we just swap the two sides of this equation, we have this formula up here. So what really happened? I know it seems like a lot of steps, but in the end, we took the first two terms and just decided to call those by our own new variables. We applied definitional logs. We applied some substitution. We applied an exponent rule, and then applied definitional log, and then some substitution again. Okay, the key step I want to point out is that a to the r times a to the s becomes a to the r plus s because of an old exponent rule. The way we had originally stated it, I believe, was a to the m times a to the n equals a to the m plus n. It's just using that old exponent law. So before digging into ways to use this formula correctly, let's also talk about ways that people misuse or accidentally use or don't think about using the formula. So let's look at some examples first. So like log base 2 of 16y. Well, the 2, so let's see, this expression log base 2 of 16y looks like the right side. So a would be 2, u would be 16, w would be y, and so we can rewrite this expression to look like more like the left side of the formula and get log base 2 of 16 plus log base 2 of y, and we might as well just do the reminder here that log base 2 of 16 just simplifies to the number 4 because this answered the question 2 to the what is equal to 16. Again here, be careful with what you say. Like this is log base 2 of 16y. Sorry, log base 2 of 16y, not log base 2 times 16y. As soon as you start saying times, people start doing all kinds of things that can't be done, like trying to distribute logarithms. So for instance, here's this is still in red. Here's an example of the type of error people make. People will see log base 2 of 3 plus log base 3 of 2 plus log base 3 of 4, and people will turn this into log base 3 of 2 plus 4, or in other words, log base 3 of 6. But that's not correct. There's no distributing or factoring, I guess, that should be going on. Instead, log base 3 of 2 plus log base 3 of 4, following what's up here in the box, a is 3, u is 2, a is again 3, oh that's good, and then w is 4, we'll get log base a of 2 times 4. In other words, we'll get log base 3 of 8. Not log base 3 of 6. So we've got to use this formula here. Don't make things up. Okay, we just showed that this formula was true and looked at some examples of using the formula and times when people go off script, so to speak, and kind of make up their own thing, which shouldn't happen. But now we're going to take this formula and do one other thing. So I'd like to consider the expression log base a of u plus log base a of u. Now, there are two ways to simplify. Log base a of u plus log base a of u. One way to simplify this is to use the formula that's boxed at the top. We already showed this formula was true, so because we trust this formula, we can now plug in a w for the u, and so we'll see that log base a of u plus log base a of, if this is a u, then we'll have log base a of u times u. So that's written here, log base a of u times u. But then u times u we could just write as a u squared. But the other way to simplify is notice that we have, again, back to this original expression, log base a of u plus log base a of u. It's the same thing twice, so we can collect like terms and get 2 times log base a of u. So these two things here, while they look different, we just simplified the same expression using valid thought processes, different thought processes, but valid thought processes. So it means that these two things here are equal. So we end up with log base a of u squared is equal to 2 times log base a of u. If we do the same kind of logic, and you should work it out, you can get log base a of u to the third is equal to 3 times log base a of u. You can also get log base a of u to the fourth is equal to 4 times log base a of u. So pattern recognition leads to this, log base a of u to the c, make sure the c is in the parentheses, is equal to c times log base a of u, and that is the third of the 3 laws of logarithms. So let's look at, again, the 3 laws of logarithms here. We've proved the first one. We're just going to skip the second one and say, look, it's similar enough with the plus turning to a minus and the times turning to a divide. And we actually applied the first formula once we had shown it was true in order to see how the third one should be true. But now let's try some warm-up problems. These questions that you're going to see in a moment seem a little bland, but we need to practice these things so that we can be set up for the next part. So let's rewrite log base 6 of r minus 2 times log base 6 of v as one logarithm. Okay, so there's 2 logarithms here, right? Log base 6, and then here's another log base 6. So first we can take this 2, which appears in front of this log base 6. That's the c here, and we can push this 2 to end up being the exponent to the input, right? So instead of c being the coefficient in front of the logarithm, c can be the exponent to the input of the logarithm. So this, leave the first term alone, we have log base 6 of r minus, and then where did the 2 move? It's now the exponent to the v. So copy the minus, but then we have log base 6 of v to the 2. And now that we have a logarithm base 6 minus a logarithm base 6, the second formula applies, and we can crunch this all in this one logarithm here. Notice the second formula had 2 logarithms on the left side and 1 logarithm on the right side. So this becomes log base 6 of r over v squared. Let's rewrite ln of x squared over y cubed using the laws of logarithms. So notice how this looks like the right side of the second formula. You might say ln, well, remember ln is just shorthand for log base e. So when you see this ln, I visually see a log base e, right? So this becomes using the second formula in reverse, backwards. We have ln of x squared minus ln of y cubed. Now, just to practice using laws of logarithms, we can actually apply the third formula, let's say forwards. The exponent 2 can come in front, and this exponent 3 can come in front of the log. And we'll have 2 ln of x minus 3 ln of y. Remember, ln of c is just notation for log base e of c. Okay, but don't write ln base little e here, okay? The whole point of writing ln, the whole point is to make it much shorter than writing log base e. Okay, let's try another one. ln of 3 times z to the 4th. I'm going to use these formulas up here. You got to be careful. It's very tempting for people to want to say 4 times ln of 3z, but that's incorrect, actually. The thing is, you might say, whoa, come on, that looks just like the third formula. Don't I just take that c that's positioned right there, like the 4, and I just bring that c in front of the log, so I bring the 4 in front? The issue here is you have to read this using the order of operations. Okay? So this actually, just to throw in a couple more parentheses to clarify, the 4, the exponent does not affect the 3. This is ln of 3, take a breath, times z to the 4th. So it's actually not in the format. It's not in log base a of u to the c format. So what we're going to have to do instead is first apply the first law of logarithms backwards, right? We've got something that looks like log base a of u times w, log base e of 3 times z to the 4th, and split this into 2 separate logs. So the sum of 2 separate logs, log base e of 3, or in other words ln of 3, plus log base e of z to the 4th, or in other words ln of z to the 4th. And now we can copy the ln of 3, and then the ln of z to the 4th term using the third law of logs. Now we can write that as 4 ln of z. So you got to be careful that everything is read using the order of operations. You can't, any formula that you use, you need to make sure that all the pieces really work with what's going on with the order of operations.